Here we will look into implementation of LSTM or BiLSTM in Keras. For that purpose, we are importing Keras package and we are using IMDb dataset, an inbuilt dataset which is already present in Keras package. So we are getting the dataset from the Keras package, and the name of the dataset is IMDb dataset. That is a binary dataset where we can perform sentiment analysis, and IMDb dataset is about movie reviews and corresponding sentiment, positive or negative. Okay, so the reviews is the text is in the form of text, and the corresponding label will be binary, either positive or negative. And sequential, whenever we define a model as sequential model, we mean that the model, the sequential model is allowing to have only one input and it will have only one output. For example, if you are considering only reviews, reviews is one input. And if along with this reviews, if you are considering an extra information, for example, user information, then along with reviews, you're also giving user information as input. Reviews are R. If R is represented as reviews and U is represented as user information, then you're considering two inputs. You're considering two different inputs. Okay, so uh, even if you were supposed to be considered, if you wanted to consider two inputs, and if you are defining your model as sequential model, somehow you are supposed to convert that. You have to do some pre-processing and make it as one input. I hope you understand one input here. I mean, one set of samples. Okay, not just one sample. Okay, one set of samples. Here, reviews is one set of samples, and the corresponding user information will be another set of samples. Therefore, if you are giving input to a sequential model, either you have to pre-process it and make it in one form and you have to give it, or else you have to take only one input. And the outcome is also one outcome for sequential model. For example, if you are trying to do something like sentiment analysis, that's done. Only one output. Okay, either it is positive or negative. But if you're doing more than that, if your label is, I mean, like, if your target is multi-label, then the sequential cannot work. That's the point here. And then we are having dense layer from Keras and bidirectional layer and LSTM layer. Here, bidirectional is when you are implementing bidirectional RNN or bidirectional LSTM, you can use this bidirectional layer from Keras and LSTM. We from Keras we are importing the LSTM layer, which has three different gates. And here next in Keras, we are also importing embedding layer from Keras. Why we are importing embedding layer is because when we are dealing with text data, we are supposed to convert the text into some vector format. So for that purpose, we can use embedding layer to make sure that we are converting text to some vector space. Okay. To convert that, we are using embedding layer here. Next, the from Keras, we are also having sequence. Here, the sequence we mean we are going to pre-process the text sequence. How we will pre-process it, we'll see when the sequence function comes. And callback is we are having model checkpoint to save the model, and that's it. So here we are loading the IMDb dataset So imdb.load dataset. And here we gave certain one parameter, number of words is equal to n words. This is because if we consider the complete dataset, we are going complete set of words, we are going to have 88,584 words in it. So to process it quickly here, we are considering only small set of words, that is 10,000. If you want to run the code with the complete set of words, you can try replacing 10,000 with 88,584. Okay. And in IMDb dataset, it is already having training and testing split. I hope you know what is the difference between training and testing data. So, IMDb dataset is already having training and testing data. So that one we are loading accordingly. We are keeping training data in Xtrain and Ytrain and testing data in Xtest and Ytest. Okay. And here to get the complete number of words that are present in the dataset, we are using this get word index and yeah. So what is this word index? Whenever we have the text data here, you see. For example, here the movie is comedy and direction is good. If this is the review comment on a movie, then how it is stored, how we are actually supposed to be storing the data. So we are going to consider the unique words in the review, right? So the unique words is movie, is comedy, and direction. Here we are also having is already there in this. So we will be writing good. So the unique words that are present in the review we have written here. So now, actually we can't consider the text as it is, right? So now what we are doing is we can keep the index to this words. 1, 2, 3, 4, 5, and 6. So now this we call it as a vocabulary, where vocabulary means it is having all the unique words in the data set. Here we are considering only one sample. So this is the small vocabulary set where we have only 6 words in it. Vocabulary means the unique set of words in the complete data set. And that each word is given an index in that. Okay. In the vocabulary. So here 1, 2, 3, 4 that we gave is index of the words. Okay. So now what we are doing is we are replacing that index for the given word. So let us see. Movie is supposed to be replaced with 1. Then we can replace is with 2. Then comedy we have 3. Then we have and 4. And then we have direction which is 5. And here we have the word is. So we can keep 2 again. And we have word good. So this is exact replacement. I mean we are converting the text to, this is not exactly the vector form. We are tokenizing this, and these are nothing but the token indexes. Okay. Here we are considering word and token to be the same. Okay. Word and token to be same here. And we are considering the token indexes or word indexes. Okay. This is what we are doing. But when we consider the Keras IMDb dataset, which is present in that, whenever we load, we are not going to get the actual text. We are directly getting this token indexes. So the process of converting, tokenizing and having a vocabulary, getting the indexes is already done and stored. So whenever we load IMDb dataset, we'll get the token indexes. Okay. So here you can see this. The list is nothing but the token indexes 162, 21044. So all these are token indexes. That whenever when we load this IMDb dataset, we are getting the token indexes. Okay. So when we get the data set, so now we already loaded the training and testing data set. Now we are going to have validation data set from the training data set. For that purpose, we are going to use train test split X train Y train. We are splitting the training data set into two parts. Where the first part is considered as training data set and the remaining is considered as validation data set. So now from the complete training dataset, only training dataset, from the complete training dataset, 20% of the training dataset is considered as validation and remaining is considered as training dataset. Okay. So now here we had training dataset, test and validation datasets, shapes. Okay. And if you print extrain, you are getting the list of the token indexes instead of the text. The process is already done and stored in the Keras IMDb dataset. And here, Y train is converted to zeros and ones. Simply, it is already zero is negative and one is positive sentiment. Next, moving on to this maximum review length. What is this and why we need this? So here, whenever we have samples, if one sample is having a length of 10 and if another sample is having a length of 35, somehow we have to fix the length, right? So to fix the length of the text, we are using this maximum review length. When maximum review length is 600, we mean that all our samples is having 600 token indexes in it. If there is no 600 token indexes, if the sample is having less number of token indexes in it, then we are going to do some padding such that we'll make the overall length of the sample to 600 tokens. Okay, to 600 tokens we are making it. Then, so to do the padding, here we have sequence. Initially we imported the sequence for some pre-processing as well. Like here what we are doing is we are padding the sequence. If the sequence is smaller, okay, if the sequence is larger, we are just taking till 600 tokens and we are leaving the remaining tokens. Okay. So here we are padding the samples with a length of 600. Maximum review length is 600. You can increase the length or you can decrease the length and try to run it. Here, after padding, if you print the X string, here the padding is happening at the initial point, which means that initially the padding bits are added. For example, if you are having a data with 4 tokens and if you want to make it to the length of 8, then what you can do, you can add padding bits. Where you have to add padding bit. Here padding bit is nothing but adding 0. So you are trying to add the padding bits zeros. Okay. Sorry, we are supposed to call it as padding token here, not bits. Padding tokens are zeros. Okay. So these tokens you can add in the initial, at the starting point of the sequence, or you can add that at the ending point of the sequence. Either this you can do, the left one or the right one. So your choice it is. So how you have to do, that's your choice. If we simply ask to do the padding, it's going to pad it. the initial starting stage of the sample. Then we are just printing the white chain shape. Okay. So now we are having that token list. We got it. We have already fixed the length and we padded it. So now each sample is having same length, that is 600. Okay. Now what we are supposed to do is we are converting this token index to some vector form. For example, if we are having a token index 49, we are going to convert that 49 to some vector form, something like this. So if we are converting this token index to some vector form, here what particular example that we considered is three-dimensional vector. Okay. In the same way, here embedding vector length is 32, which means that we are trying to have a vector length of 32 dimension. Okay. So now we are converting the token index to a vector form of length 32. Okay. So here you can choose either 32 or 64 or 128, 350, whatever you want, you can try. You can change these values and look at it once. And then, so we are defining that model is sequential, just having only one input and will have only one output. And now, so we are supposed to convert total 10,000 because in our data set we are considering only 10,000 words in it. So obviously we'll have only 10,000 token indexes, right? Therefore, for the 10,000 token indexes, we need to have some vector representation. That vector representation is of length 32. So we are having an embedding layer to convert token index to some vector length, each token index to some vector length. Okay. Once it is done, we are passing the input and we are converting each each input token index to the corresponding vector form. And once it is done, here the outcome after embedding layer is three-dimensional. Okay, what is those three dimensions? First dimension is batch size, whatever batch input that we are passing it, that is first dimension. Second dimension is sequence length. What do you mean by sequence length? We fixed the sequence length to be 600. So the sequence length here is, so the dimension length, sequence length will be 600. If you are fixing the batch size 4, then 4 comma 600. And next one is embedding dimension. So here, if your batch size is 4, then your output from this embedding layer will be, okay, this will be your output from the embedding layer. So once you get this output, you are passing this to the LSTM layer. So simply we are adding the LSTM layer to the model. And in the LSTM layer, it is having the outcome of LSTM layer is going to have 100 dimensions. Okay. And the important parameter here is return sequences. If your parameter return sequences is false, which means that you are not going to consider the outcome. You're not going to consider the sequence output. Your output will not be a sequence. Your output is a vector, two-dimensional. Here actually your input to the LSTM is three-dimensional. Okay. But if you are considering written sequences as false, then your output from LSTM is going to be two-dimensional. Okay. If in case if you are considering written sequences as true, then your output dimension is three-dimensional. That is nothing but batch size, comma 600, comma 100. The 100, this 100 is nothing but the 100 that you placed here. If you keep here 50, then you will get the dimension 50 here. Okay. The dimension value is 50. This is for LSTM. If you are using BiLSTM to implement BiLSTM, the only thing that we are supposed to do is bidirectional of LSTM. Nothing more than that in Keras. So this is your bidirectional LSTM layer. If you are implementing bidirectional LSTM, then the outcome when the return sequences is true is by batch size, comma 600, comma 100 plus 100. Why this 100 plus 100 is because you are having two directions, left and right. Bidirectional means two directions, left and right. So from the two directions, you are getting the hidden state information. So it is 200. Okay. This is for written sequences. Why? What is this written sequences and why the written sequences is playing the role? Let us look into it. Whenever you have input X, you are passing it to some LSTM block. Okay. When you are passing to the LSTM block, you can take output Y1. Okay, if your input is X1, you can take output Y1, right? But you can also have like this Y2 for this X2. Okay. Here, if you observe here, when you have the sequence X1 and X2 values, I mean like values means here tokens only. So here X1 and X2 are tokens and you are passing one token to LSTM and the outcome you are keeping it and you are passing another token to the LSTM and the outcome you are keeping it. This is one way, which means that you are having outcome Y1, comma Y2. Okay. This is your output sequence. Output sequence. In the same way, you can also have, instead of taking outcome from X1, you can simply take outcome from Y. Uh, you can take only the last outcome, Y2, which means that this is a single vector which has information about both X1 and X2. Okay, so this is a single vector which is having information from both x1 and x2. Why I call this as vector is because we are considering here only one single sample. Okay. Yeah. So this is, if your return sequence is false, then you are going to get this outcome. If your return sequence is true, then you are going to get this outcome from the LSTM. Or if you are implementing bidirectional LSTM, from the bidirectional LSTM. Okay. So once here we kept written sequences as false, so we'll get the vector for each sample, and that is passed to the dense layer. And here we are considering the final outcome prediction we are trying to do by using the activation function sigmoid. Okay, so this is the model that we are going to define. Model dot add is nothing but we are adding a layer to the existing model. Here we define model as sequential. So we defined it as sequential and the model is empty. Once the model is empty, we are adding embedding layer to the model. So it has embedding layer. After embedding layer, we are again adding the bidirectional LSTM layer. So the next one is bidirectional LSTM layer. Therefore, in this way, we are going to add all the layers. How many times you want to add the layers? Whatever the layers you wanted to add, you can add. Okay. And now model.compile. Here we are defining the loss function because our outcome is binary. So we are going to use binary cross entropy loss. And optimizer, you can define any optimizer or atom optimizer. Here we are using RMS prop or SGD, whatever you want it to use, you can use. And we are considering accuracy metrics. Okay, file path. So to store the model, we are giving a path, and the path name is weights.keras. In that file, we are going to store. And when to store this weights into the path, file path. Weights, we mean nothing, model, whatever the model is, nothing but weights and bias, right? So we are supposed to store these weights and biases. For that purpose, to store the weights, when to store the model weights. So to store the model weights, we are considering a condition that is validation accuracy. When the validation accuracy is maximum or more, then the model weights should be stored in the specified file path. Okay. Whenever the validation accuracy is more, then the model weights should be stored in the specified path, and we already defined it. Next, model dot fit. Now we are actually, till now what we have done is we designed the model, we added the layers to the model. We had a model now. When we had a model, now we are going to train the model. The model.fit function is going to train the model where we are passing X train and Y train and epochs, the number of epochs, whatever the number of epochs you want to try, you can. And batch size, here we consider 256, and verbose is nothing but how this display will be when it is executing. That's it. It's not affecting anything in the training or for the model. It is just how to display the training process. Here you can see this bar, right? This bar, when you mention this verbose as one or two, then only you can see some procedure like this. If you don't mention it, you can't see this bars, simply it executes. It's just a visual thing. Okay, next callbacks list. Now we are considering that when to save the model, that condition we are placing it here, and we are considering the validation data. Validation data, we already split it. Okay, so now we can fit the model with the training data. Okay, and once the model is trained, it will be stored, and uh, you can load the weights, and by using the same binary cross entropy loss, you can consider the model dot evaluate to evaluate the model on the test data, how it is performing on the test data. Okay, and you can print the accuracy. So now let us start executing from the beginning. Okay, and also observe here the left side part. So here in the left side part, we are having a sample data folder only. Okay, once we execute, we'll see what happens. Okay, okay, this is something. Yeah. Now data set is loaded, and the data set is loaded, and here it's a comment actually. This is also a comment. This is just a shape. Here you can see how to pad from right side onwards. And here this one. And now each epoch is running, training is going on. And okay, so meanwhile, we can also have PyTorch stars to use to implement LSTM, and you can have the glance once. In this code, we'll try to load a CSV file and try to implement the same BiLSTM or LSTM layer. Instead of LSTM, you can also have RNN. Simply, you are supposed to write here. You are supposed to import RNN layer from the Keras, and here simply if you use instead of LSTM, if you replace with RNN, then it is nothing but your bidirectional RNN. Okay. So this is one thing. And also, if you are having here written sequences true, you can also have one more layer with bidirectional LSTM because your output is also a sequence again. So for the sequence again, you can have another bidirectional layer or unidirectional simple LSTM also you can have. So you can stack these layers. This is stacked LSTM or stacked BiLSTM you can tell, and you can add on. Every time you can take the sequence output and you can have multiple such bidirectional LSTM layers here. Okay, and another thing is recurrent dropout. So recurrent dropout here actually in RNN or LSTM, we are having a loop. When we roll back that loop, we'll get different hidden connections in it, right? So when we are having such different hidden connections, we are going to have dropout. That dropout when we roll it, when we are rolling that LSTM layer and when we are using that dropout for that loop, then that dropout we call it as a recurrent dropout. Okay. And also here optimizer is if you are having if you are mentioning Adam simply, it will take the default learning rate it will consider. Okay, if you wanted to change the learning rate, if you want to specify your own learning rate or whatever, you can call like this. Just look at the syntax properly and you can call. Okay. And here you can see the first epoch is already done. And see the validation accuracy from minus infinity. Initially, the validation accuracy without any training, the validation accuracy is minus infinity. And after one epoch of training, the validation accuracy came to 0.81, which is higher than minus infinity. So when the validation accuracy is more than the existing, then save the model weights. Okay, then save the model weights. So here, Validation accuracy is improved from minus infinity to 0.81. Therefore, we are saving the model to the specified file path weights.keras. So here you can observe a file named as weights.keras is created, and the weights are stored in that file. Okay, so we'll see whether the second epoch is going to be saved or not. You can also have one more point like not validation accuracy. You can try to have validation loss also. Instead of validation accuracy, you can save the model with respect to validation loss also. So you can mention that point here, like monitor validation loss instead of validation accuracy. And the saving mode you have to do minimum. When the loss is minimum, then only you have to store it. So here, in the second epoch also, the validation accuracy is increased. Therefore, again, the model is saved. Here, it is just replacing previous model's weight with the current, it is just changing, replacing the previous epoch weights with the current epoch weights. We are not taking the extra space, it's not we are not saving it multiple times. In one file only, we are replacing the values every time whenever we get the validation accuracy mode. And here is the final epoch. So these values, all you can change. You can change the embedding dimensions, and you can try. You can add on different layers. You can try different things, and you can change the loss functions. You can try uh, different padding sequences, and you can also increase the data number of tokens in the dataset and try different variations to have proper understanding. Also, you can try different activations also. Here, instead of activation sigma, you can also try the softmax activation also. So here, if you observe, the validation accuracy is increased. At the same time, validation loss is also decreased. There is no such rule like whenever the accuracy increases, the loss will decrease. And whenever the loss decreases, accuracy must increase. There is no such rule. So you can consider either accuracy or loss for saving the model. And here also, after third epoch also, the validation accuracy increased and the validation loss decreased. So now the final weights of the model are coming from the third epoch. You can increase the number of epochs and check. Okay. So now the model training is done. So we are going to load the model and test it on the test data set. Okay. The values that you're seeing is for each batch. Okay. The final one you will get. Yeah. So final accuracy is